Hi everyone, welcome to Vedantu JEE English. I'm Diksha Ma'am, your chemistry master teacher, and today is the last lecture of coordination compounds, right? Because we have completed everything, right? We have completed nomenclature, classification, we have completed CFT, VBT theory, everything is done, right? We are left with isomerism. And if you see, ma'am, isomerism, ma'am, is it a like very big topic or a very small topic? See, in NCRT, you will see hardly one page on isomerism. Usually, I say that yes, isomerism, NCRT is the best book. You should go through NCRT. Every single line is from there. But when you talk about isomerism, it is not given. Actually, 1 2 paragraph is given, right? And from that, you have to identify, right? Which surely is very difficult to do that, right? So that's why I am saying that this lecture is going to be very important for you, right? Because I'm going to teach you with everything that you need, right? So all these atoms, molecules, right? How there is plane of symmetry, how there is isomerism possible or not, what is geometrical isomerism. See, usually we tell students that, okay, imagine this, imagine that, right? But today I'm going to teach you how to visualize. I'll show you the structure. From that, you yourself will tell, right? Now, the question might arise in your head is, ma'am, but the structure will not be given. They will not provide a 3D structure in the exam, right? So I'm also going to give you some tricks from which directly you will get to know which has how many isomers, right? And I'm also going to give you a table, right, of geometrical and optical isomerism, those students who want to revise it on the last, right? So everything that you need will be here in this particular lecture, right? Okay. So everybody, last time I gave you homework, right? But before that, yes, one thing is, if you talk about isomers, that is actually everywhere in our life, right? Everywhere, right? You talk about, we eat isomers daily, right? Ghee, butter, curd, right? These all are isomers, right? So dairy products give vitamin B12, which is a mixture of different isomers. And we are also going to discuss that how come B12 actually exists in 7 different isomers, right? That is just an additional information that I'm giving you, that B12 exists in 7 different isomers, right? This is what we have. So in our daily life, we have isomers, right? It's not like something we are studying which is not even there in reality. It is there in the reality, right? So this was the homework, guys, that I gave you, and this is the solution of the homework I have attached here, right? You can check that if you have like done the homework. If you have not done it, I can't do anything about it, right? All I can say is that, guys, do the homework, right? If you don't do it yourself, then how you will get to know that if you're good at it or bad at it, right? Okay, now let's understand isomerism, right? Isomerism, what exactly is isomerism, right? Isomerism is that thing. We have studied isomerism in organic chemistry, also we'll study that. So isomerism is basically when you have same molecular formula, but its structure or its spatial arrangement will be different. What do you mean by that? So let's say I have a formula like XYZ. This is the formula, right? How it is arranged, right? That means you can think about a doll, right? You can think about a doll and you can think about a human being, right? So if you talk about a doll, right, you can, take out its head, you can take out its arm, you can take out this arm, you can take out the legs, right? So you can actually twist the leg, you can twist the head, right? That's what you can do with the doll, right? Annabelle doll, you can say, doll, you can do everything like that, right? So that means you can actually rotate the thing, right? So for example, for a doll, you can twist the arm, but for me, you cannot twist the arm, right? So this is actually structural and stereoisomerism. In structural isomerism, I am saying that what you have to do, the linkage has to be same, but you just need to, okay, so let's do one thing. Firstly, let's discuss about structural isomerism. Okay, so I'll give you a proper example of that. If you talk about structural isomerism, it's simple that if I talk about a doll, right? If I talk about a doll, right? You can change its position, you can change its linkage, right? You can change its linkage. Some, we all have done this when we were kids, right? So we used to change the head and put it somewhere, right? We used to twist the arm and we used to break the arm, right? These all things we can do with a doll, right? But with a human being, right? With a human being, you can't be like, oh my god, my head is paining a lot. I'll just twist this head and take it out today. Oh my god, my arm is paining a lot. Let's twist this arm and take it out today. You can't do that, right? So what you can do, oh my god, my head is paining. All you can do is you can rotate it like this, right? So you can't take out, you can't change the position, you can't change the linkage of your body. You can't be like, oh my god, my arm is paining. I will put arm on my leg side. Okay, I'll put my head here on my knees. No, you can't do that, right? You can't change your position, but you can definitely change your spatial arrangement. I can rotate my neck, I can rotate my arms, right? That is spatial arrangement, right? So there are two kind of isomerism that can exist. One is the change in the linkage, change in the position, all these things, but the molecular formula has to be same, right? Second is stereoisomerism. Here you can only change the spatial arrangement, right? You cannot change the linkages. You cannot change the linkages. You can only change the spatial arrangement. I hope so. This thing is now clear to all of you, right? Yes, future IIT, I know, yeah, that you did the homework, right? That's very good, right? Okay. Will you start thermodynamics or organic chemistry for class 11? Yes, Bhanu Sai, I'll definitely start, right? Do let me know if that thing is clear, right? Now, let's move towards structural isomerism, which is very simple, right? It will hardly take me next 15 minutes to cover structural isomerism. And the questions, right, are sometimes asked from structural isomerism, but mostly from stereo isomerism, okay? So firstly, I'm going to cover structural isomerism. Structural isomerism is, right, of so many types, right? Let's discuss that. Structural isomerism is due to difference in the type of chemical linkages, whether X is connected to Y, X is connected to Z, right? These are structural isomerism. Or maybe somewhere Y is connected to Z and then Z is connected to X here, right? So there are different type of chemical linkages that you have, right? And the distribution of ligands within and outside the coordination complexes. Now, if you see, there are like total 7 types of structural isomerism, actually 6 types. 1, 2, 3, 4, 5, 6. Right? All of them are not written in your NCERT. That's why I'm saying today I'm teaching out of NCERT as well. In an NCERT, enough is not given, right? So, if you talk about first is ionization, then there is hydration, which is also called as solvate isomerism. Then there is coordination, linkage, ligand, and coordination position isomerism, right? Let's talk about this one by one. First is ionization isomerism. If you talk about ionization isomerism, right, it means the counter ion will be different here, right? So these two are the ionization isomers of each other. Here the counter ion is Br, here the counter ion is SO4. Here Br is acting as a counter ion. Here Br is acting as a ligand. Here SO4 is acting as a ligand. Here SO4 is acting as a counter ion. That is the difference, okay? So, it's a potential ligand and can displace ligand, which can then become counter ion. That means this Br, it is only shown by those ligands which can also behave as counter ions, right? So that's why there is replacement of ligand and counter ion in the two isomers, right? That is called as ionization isomer. Why? Because here the ions will be different. Here it will give this particular ion, that is CONH3 and 5SO4 plus Br negative, right? And here it is going to give a different ion, that is CONH3, because the ions are different, okay? The counter ions are different. If you see, this is going to give you SO42 negative, because the ions are different, that's why it is called as ionization isomerism. Second category is hydration isomerism. So in hydration isomerism, there are some water molecules which will behave as ligands and will also behave as water of crystallization, right? So if you see this here, this one, and this one, these three are hydration isomers. Here you have 4 water, here you have 5 water, and here you have 6 water. Here you have 4 water as ligand. Next, other 2 H2O are acting as water of crystallization. This is okay. Here also you have 5 ligands and 1 water of crystallization. Here you have 6 ligands. So if you see in total in all these 3 molecules, you have 6 water only. But here 4 is acting as ligand and 2 is water of crystallization. Here 5 is ligand and 1 is water of crystallization. Here you have 6 as ligand and you have 0 water of crystallization. So this kind of isomerism is called as hydrate isomerism, when there is difference in the water molecule acting as ligand and water of crystallization, right? Okay. Now, next is going to be coordination isomerism. So in coordination isomerism, let's see what you will have, right? In coordination isomerism, you have 2 things. This is the bracket that you will have, and this is the bracket that you will. In coordination, always you are going to have 2 coordination brackets, right? So here, what will happen? I'll show you that with the help of an example. This is a coordination. These 2 are actually coordination isomers of each other, right? What you will see here, here you have chromium, but here you have ammonia as the ligand, right? Here you have cobalt and here you have ammonia as the ligand. Here you have cobalt and here you have CN as the ligand. Here you have chromium and here you have CN as the ligand. Can you see one thing? That here 6 ammonia is attached with Cr, but here 6 ammonia is attached with CO. Here 6 CN is attached with CO and 6 CN is attached with Cr. That means what we are doing, we are exchanging the ligands here. We are exchanging the ligands here. When we exchange the ligands in 2 coordination brackets, that is called as coordination isomer, right? So, complex has 2 complex ions, right? 2 brackets you will have. One is cationic, one is anionic, and it arises by inter-exchange of ligands between cationic and anionic entities. These cationic and anionic entities are exchanging the ligands, right? That's how you have the coordination isomerism, right? Third isomerism. Next is linkage isomerism. It's very simple, right? So linkage isomerism is always shown by ambidentate ligand. How many of you remember what are ambidentate ligand? Let me know. Ambidentate ligands are like NO2 and ONO, which are having 2 donating sites, right? You have two donating sides, but at one point you will donate from one side, right? You have two donating sides, but at one point you will only donate from one donating side. Okay, that is ambidentate ligand, right? Now, here if you have an ambidentate ligand like this, you have NO2. Here it is donating from nitrogen, so that's why color is yellow, right? So it is why it is called nitrito N. But if it is donated by ONO, that means it is donating by oxygen, it will be nitro O, nitrito O, and this is red in color. That means these two are different compounds, right? And they are existing because the linkages are different. That's why it is called as linkage isomerism. Okay, everybody? Very good. Okay, perfect. Next is ligand isomerism. What is the ligand isomerism? In this, ligand is itself an isomer, right? So what you will see, here you have this ligand or you have this ligand. If you see, the formula of these two ligands are same. Here, ligand is isomer of each other, right? So this ligand here, you have NH2 connection here at the third position, and here you have NH2 connection at the second position. So when these two ligands are there in two separate things where everything else is same, that will be called as ligand isomerism, right? So here it is saying that many ligands are organic compounds which have possibilities for isomerism, and those ligands will show you ligand isomerism because the ligand itself is existing in isomerism, right? Last one, this is one of the examples of ligand isomerism. They can ask you this in JEE Advanced as well. You know, it's not like they will ask you this question directly. Definitely some part of some question it can be, right? So vitamin B12 has total 7 isomers, right? And this is one of the isomer that it is showing, right? So vitamin B12 have different ligand isomers, right? Okay, vitamin B12 that we need that has 7 different isomers. It's just a extra point that I'm telling you, right? Okay. Last one is coordinate position isomerism, right? So here what you have in polynuclear complexes, an interchange of ligands between the different metal nuclei gives rise to positional isomer. So basically what is happening here, right? So there are so many nuclei here, polynuclear it is, right? So in this this is a polynuclear complex, right? These are polynuclear complexes. So here what is happening, there is an interchange of ligand. Like here you have 2Cl2 in this position, right? And here you will have one Cl here and one Cl here. So that means it is see, because we are saying that the ligand position will interchange inside the coordination complex. So that is why it is called coordination. And here the position is changing. So that's why it is called coordination position isomer. Very rarely you will see this somewhere, but yes, that was important for you, right? Now, Richa, we are going to discuss about stereo isomerism. Very important, okay? Let me know. Thank you. Okay, now please study also, right? Okay, so guys, we have stereo isomerism. Acha, tell me one thing. Are you scared of stereoisomers? Right? Because it's very interesting. For me, this is one of the favorite topics, right? I genuinely love this topic, right? Why? Because students find it like, oh my god, ma'am, such a tough topic, ma'am. I don't know how will I do it, right? This and that. But when you actually understand this, this is so simple, right? So let's understand, right? And trust me, you are going to love this, but you need to have patience here, right? Because next 1.5 hour I need of yours, because this topic I can't teach you in 30 minutes, right? Otherwise, I'll be lying to you. Actually, this, if I like take it very, very slowly, it will take me around 4 hours to complete it, right? But because I am teaching you in that manner, because I have written everything here to save the time, right? So yes, it will take me less time, but if I teach you on a blackboard, then definitely more time it will take. Right? So it's a lengthy topic which I'm trying to take as less time as possible. But still, you have to promise me that you will be here till the end of the lecture. Right? That's my promise to you. You will learn something out of it, and you are going to thank me in the end. That's my guarantee to you. Because very rare teachers teaches this topic the way I'm going to teach you, right? So that's why be here and have patience, right? Okay. So in stereoisomerism, right, like we discussed in organic chemistry also, spatial arrangement is different. Your neck is like this, your neck is like this, your neck is like this, your neck is like this. It's not like you can just take out your neck and place it somewhere else, right? You can rotate your neck, right? So your spatial arrangement of your arms can be different, but you can't pick out your arm and place it somewhere else. That is stereoisomerism, right? When you can just rotate, you can just do spatial arrangements, right? It is of two types. One is geometrical, other is optical, and one by one we are going to discuss this, okay? So we are going to discuss both of them in coordination number 4 and coordination number 6. Acha, tell me one thing. Coordination number 4, you have two kind of things, right? Two kind of geometries. One can be tetrahedral, other can be square plane. Okay? Then this can be octahedral. 6 always is octahedral, whether inner octahedral or outer octahedral. It's always octahedral, right? And here also it is tetrahedral and it is square planar. So we are going to discuss this in all the cases, right? Let's start. Firstly, I'm going to teach you the geometrical isomerism for all the cases. Then we will discuss optical isomerism for all the cases, right? Let's focus on geometrical isomerism first. Yes, everybody, tell me, let's focus on geometrical isomerism first. Right? Now, geometrical isomerism, firstly, I'll be teaching this. As you all know, I have like tonsils, so that's why my throat needs some rest now. Okay. Now, guys, firstly, what we have is square planar, right? Now, we are going to discuss this the way we should be, right? So, firstly, we are going to talk about geometrical isomerism that exists in square planar. This all you don't need to know. Firstly, let's discuss tetrahedral complex, okay? So, how does a tetrahedral complex looks like? 1 and 2 and 3 and 4, okay? So, that's how a tetrahedral complex looks like, okay? So if you see, we are saying that tetrahedral complex is never going to show any geometrical isomerism. For that, you need to understand, ma'am, what is this geometrical isomerism? See that. If I have any structure, I am taking here square planar, right? Geometrical isomerism is of two types. One is cis, one is trans, right? Raksha Bandhan, how many of you celebrate Raksha Bandhan, right? Raksha Bandhan. It's about brother and sister, right? So if you have a sister, you must know that sisters are always like, they always care for you. Sisters are like mothers, right? They are your second mother, right? So they always care about you. So sisters are always together. They will always stick by you. They will never leave your side, right? So similarly, cis means sister, and sister is never going to leave you. She will always be by your side, no matter what. right? So here, same kind of ligands will be side by side. Trans is opposite, right? Here, same kind of ligands will be on the opposite position, right? Same kind of ligand will be side by side. Same kind of ligand will be opposite position. Now, I just showed you the example here. Now you tell me one thing, right? This you can only understand by actually looking at this diagram, actually looking at this figure. Okay, first you tell me if you're able to see this. Tell me one thing. If I have, let's say, a different ligand, I'm taking different ligand here, okay? If I put this ligand here, right? Or you can say if I change it like this, will it change anything? No, right? There is no case of opposite to each other because all are at same angle. This is at same angle 109. This is, sorry, 104, 104, 104, 104. If you place it like this, does it make any change? If you place it like this, does it make any change? If you place it like this, does it make any change? Or I will show you like this, right? You tell me one thing. This is the tetrahedral complex. Now I will put this particular atom on the upper side. It's the same thing. Now I'll put this particular atom on the upper side. Same thing. Now I'll put this particular atom on the upper side. Same thing. Now I'll put this particular atom on the upper side. Same thing. Now I'll put this particular atom on the upper side. Same thing. This particular atom on the upper side. Same thing. Can I get any different thing here? No, right? So there is no opposite here, right? We can't say these two are opposite to each other. See, angle is 104. So how they can be opposite to each other? These two are opposite. There is no opposition here, right? All of them are at 104 degree. There is no as such. See, for opposite thing, you need to have 180 degree angle. So there is no atom which has 180 degree angle. There is no two atom which has 180 degree angle. So we can't say they are opposite. So they will have trans, they are on the same side, they will have cis, because every single, because this particular atom, if I make a different atom here, this atom is next to this one also, is next to this one also, is next to this one also. Okay. Now you say, ma'am, change all the atoms. Okay, I'll change all the atoms. Okay. I'll change all the atoms. Okay. Now see. This atom is next to green one also, yellow one also, and white one also. If I put it like this green is next to this yellow also, white also, brown also. If I put it like this white one is next to green, yellow, and brown, all of them, right? So every atom is next to all the atoms. So there is no possibility of cis and trans here. Can you see? There is no possibility of cis and trans. So that's why here we are never going to discuss cis and trans. They can never show geometrical isomerism. Cancel. Okay. So here you can put it here. Tetrahedral is never going to show cis and trans. Now let's talk about square planar. Simple, easy, right? Let's see that. Okay. This is a square planar structure. All of them are at 90 degree with each other. 90, 90, 90, 90. Right? We usually call it like this. Right? Now, let's understand that. Firstly, I'll have MA4 kind of structure. Okay? 1, 2, 3, 4. This is M, this is A4. Can you see white, 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 white? All of them are same. So there is no opposition. White is opposite to white, white is next to white also. There is no cis and trans you can see here. So there is no geometrical isomerism here. Okay? There is no geometrical isomerism here. Next is replace one atom with some other atom. Okay, so I am going to replace it with some other atom like B. Now, this A and A are opposite to each other. Can you see that? Everybody in the chat box. Let me just wear the specs as well or not. Okay. Yes, everybody. If you see this here, right, this is opposite A and A, but A and A is also cis. This is also next to each other. This is also opposite. So there is no link of cis and trans. So there is no cis and trans isomerism, no geometrical isomerism between when you have this thing. There is no change as such, right? This is also cis, this is also trans. No change. Next is MAB3. If I say that this is A and this is B, okay? This is B. Again, these two can be trans, but these two can also be cis. So there is no point of cis and trans, no GI. Next is the A2B2. Okay, you will have two same atoms and two same atoms. See, these two atoms, A are opposite, B are opposite. This is a structure where you have, this, students, is a structure where you have trans or cis. Tell me that. Was it trans or was it cis? Everybody in the chat box. Was it trans or was it cis? Because now I'm going to draw something else for you, right? Let's draw that. Wait. Chalo, that's not possible. It's okay. Okay, so that is opposite. Opposite means trans. If I put this green atom next to green atom and this white atom next to white atom, so now this is a cis structure, right? They are next to each other. So shall I say this is a structure where you have cis, right? So this is an example where two same ligands are opposite. Two same ligands are not opposite on the same side, that is cis. Two same ligands are opposite. Two same ligands are opposite, that is called as trans. Here it is possible, right? Next possibility is, let's talk about Ma2BC, right? So here we are saying that you have Ma2, Ma2, 2A you have, I don't know who is this rat or cat here, 2A you have here, and you have B and C. So there is some C atom also here. So I need to draw some C atom also here. I am drawing that. Okay. Here, can you have any possibility? Everybody in the chat box. If I say these two green atoms are next to each other, and I can also draw it like this. I can also draw it like this when these two green atoms are opposite to each other. Now these two green atoms are opposite to each other. So cis and trans is possible, right? So cis and trans, you can see the possibilities here. So when two same atoms are next to each other, it is cis. When two same atoms are opposite to each other, that is trans, right? Next is MABCD. Let me see if there is anyone. A2B2 we have seen. A2B2 we have seen now. A2B2 we have seen. Then we have seen A2BC. Then we will see ABCD. Okay, ABCD. Now this one is very interesting. Okay, for that I also need one extra page to show you that, right? Because this is actually a tricky one, right? And this is very frequently asked. Very frequently. Here they are saying that this kind of situation you have. Now tell me, will you be able to predict? Because there is a trick to predict this. This was predicted by a trick. Okay, predicted experimentally, right? It was seen that it has 3 geometrical isomerism. But how? The question is, Ma'am, how it can have three different geometrical isomerism? Okay, so I'll show you that, right? Let's talk about this thing, right? So by this extra page, I'm going to write everything here. So this is M, this is A, B, C, and D. Guys, see this very carefully, note it down that how we are going to see this, okay? How we are going to understand. This is again draw M, again draw M. So how it can have three isomers? So what you will do, you will have to fix any of the atom here. I'll fix A, okay? I'll fix A. This is a trick, okay? This is A, this is A, right? I'll fix this. Now what I'll start doing, I'll start interchanging other two things. So I'll firstly interchange C and D. So this will become D and C. This will stay as it is, right? This will stay as it is. Now I will interchange B and C, and this D will stay as it is. This will be C and this will be B, right? And these are the three isomers. You will say, ma'am, how these are the three isomers? Another trick, right? So once you have drawn these structures, after this what we will do, we'll take any of these two as same, right? So you can take, assume, anything you want me to do in the chat box, okay? You can write it down in the chat box. Whatever you want to take two things equal, which can be A or B, ma'am take C or D equal, ma'am take B or C equal, ma'am take A or C equal, anything. I'll see the first comment and I'll do that. Yes, everybody. I am waiting for your answers. Not even answers for your assumption. Yes. A and C. Okay, I'll take A and C equal. A and C equal. So if I take A and C equal, I'll make a box here. I'll make a box here. I'll make a box here. A and C are next to each other, that means it will be cis. A and C are opposite, that means it will be trans. A and C are next to each other, it will be cis. No matter you take A or D equal, you take C, D equal, you take B, D equal, any two you take equal, always and always for M, A, B, C, D, you are going to have three isomers, out of which two will be cis and one will be trans. And this is a direct question that can be asked to you. Okay? Always, whatever you take equal, always it is going to be two cis and one trans. Always and always. Right? Okay? Tell me, students, if you have any problem in this case. Any problem here. Right? Next one is MA2, MAB2. Okay? Let's take this. MAB2, let me see how. Okay, I'll have some other also. Right? MAB2. Okay, before that, I want to teach you something regarding MAB2. So, guys, basically we have two kind of bidentate ligands. Okay? One is symmetrical, other is unsymmetrical. Bidentate ligand. We have two types. One is symmetrical, other is unsymmetrical. For example, you must have seen EN, that is nothing but CH2, CH2, NH2, Can you see this is exactly similar, like symmetrical? For example, you have oxalato. Okay, this is COO negative, COO negative. Can you see these are symmetrical? Unsymmetrical are like you have glycinato. Okay, so here what you have is CH2, COO negative, and NH2. Can you see it is unsymmetrical? Here you have CO, here you have NH2, and these are symmetrical. So what we do is we represent symmetrical ligands with AA or BB. We represent the unsymmetrical ligands with AB. This is how it is represented. This is represented as AB, or not even this one, the simple AB. These are your unsymmetrical ligands, and how I am going to draw that? When I'll teach you now, I'll represent AA or BB like this, where both sides you will have same atoms. That's how I'm going to represent, okay? This is BB, right? And AB, I'll represent it like this, okay? So that's how we are going to see. Let's understand. Now, let's talk about AB2. So here you have two ligands which are unsymmetrical, okay? Which are unsymmetrical. So two unsymmetrical ligands you will have. I'll also carry two unsymmetrical ligands here, right? These are, wait a minute, two unsymmetrical ligands, right? AB, AB. Now see one thing, what we will do here, right? We are going to make a square planar with these things, right? Oi hoy. I wish we had undo button in our real life. Really wish. Now, if I put this B here and this A here, right? This is little tough, or I can actually do like this. Okay, AB, and this is B. Tell me, guys, is this cis or trans? Is this cis or trans, everybody? Is this cis or trans? Is that possible? Here, two same are next to each other. Here, two same are next to each other. If I draw it like this, that's the most irritating part of this lecture, that, you know, it's very easy to say, okay, I'll do that. But, you know, I don't have like 10 sets of atom. I have only one set. I'm a poor person. Only one set of atoms I have, right? So, this is opposite. So, can I say cis and trans is possible? Yes, ma'am, definitely it is possible. So, you can write it like this. M. How we write it here? EE, and this we mark it like this, that they are linked to each other. This is BB. Okay? Or M, this is actually AB now. So this will be AB, this will be BA. Or this will be AB and this will be AB. Now if you see this, A and A are opposite, so this will be trans. A and A are next to each other, this will be cis. That's how you're going to have cis and trans. Next is you will have AB2. Achha, this we have done. Now other is AB2 we have done. AA and BB. Achha. Now let's talk about AA and BB. Okay. So I'm going to write some things here. Right. For that, what I'll do, I'll just delete some things here. Okay. Sure. Now, let's do this. This one is MAABB. Now, who can predict this? MAABB. Instead of showing you This in 3D, it's not actually that needed. It's very simple, right? So it's AA and BB. AA is connected, BB is connected. Now, can I make something else also? If I make MAA here, if I change this, this will remain the same, no? BB. If you want to see this, let's see this, okay? Let's see this. Just give me a second and I'll make AA and BB ligands for you, right? This is AA and this is BB ligand, right? So when you put AA ligand here, this is AA, okay? And this is BB, B and B. So this is AA, BB, right? Now if you see this here, this is AA and this is BB, right? Okay, ma'am, interchange this. How can I interchange? Okay, I'll interchange. It was like this, I'll change it. This is AA. Has anything changed here? If I change this, it will remain similar. If I change the positions, it will remain like this. If I change this, it will remain like this. Okay? So there is no cis and trans possible here. So I'll just directly say no cis and trans, no GI possible. Right? Next one is you have AA and AB. Or firstly, I'll draw MAA twice. Obviously, there will be nothing possible here. Nothing will be possible here. This so you can tell very easily, right? Without even me drawing it, you can tell that. This is, anything is possible. You rotate this, whatever you do, nothing is possible. You interchange this, you interchange like this, you rotate it, nothing is possible, right? So, here we can say, again, no GI possible. Next one is MAA and AB, and this is the last one for square planar, okay? MAA and BB, AB. Okay. Now, let's do this and tell me if any GI is possible. Is there any GI? See this very carefully, okay? If I interchange this is AA, this is AB. If I interchange this, I'll have this thing. Which if I rotate, it will become the same thing. No change, right? No change. So again, I'll say no GI possible. Okay? All the possibilities we have discussed, guys. Right? Now I'll talk about coordination number 6. Ready, everybody? Ready, everyone? Coordination number 6. Right? Ready, everybody? Let's talk about coordination number 6. Right? Let's talk about coordination number 6. That is an octahedral species. And for octahedral, let's understand, it is like very simple also. This is also not difficult, right? So here you have this kind of situation. Two opposite, and two opposite, right? Now, what I'll do, again, cis and trans we'll talk about. So, his trans pair means if any octahedral compound has one trans pair, it is going to show cis and trans isomerism simple. Okay, this is what it is written here, right? Now, if you talk about, if I say 1,4, okay, so I'll just right? 1, 4. Okay, I'll just draw some different atoms here, right? 1, 2. This is green I have, and then I have one red, and then one, oh, we have one brown. Okay, we have one white as well. That also we have one purple as well. Okay, right? So this is what you have, right? This is what you have. Can you see this? This is your octahedral. So he is just talking about the trans pair here, right? Can you see the trans pair, guys? Trans pair is this red and blue is trans pair. Similarly, he is saying 1 and 4. I'm not getting into 1 and 4. I am giving you by simple visualization. Red and blue is trans pair. Green and brown is trans pair. Black is trans pair with this purple. Okay. Opposite one are the trans pairs. Okay. Opposite are the trans pairs. Right. Now, let's discuss about when you have all the monodentate ligand A, B, C, D, E, F. The question is, right, first is ME6, right? That means you will have all the 6 same. Now, how many of you can tell me just by imagining this, right? That you have all of them as same. Is there any possibility of cis and trans? Students, if any of them is same, no, there is no possibility of cis and trans. How can you say that is possible? Right? There is no possibility of cis and trans here. Can you see that? There is no possibility. Even if you change, if I change this with this one, right? Nothing is going to happen. It will remain the same only. Right? So there is definitely no GI possible here. Next is MA5B or MAB5, right? That means you have to replace one with some other. I'll replace it with this red one, okay? Now, if you see, if you find any trans pair, then it is possible, okay? So if you see this here, is there any possibility here? The simple thing is, if you see this red one is cis with all of them. It is trans with this one, right? Even if I replace it here, say, ma'am, replace it, I'm replacing it. It is the same thing. Now I have same thing. Ma'am, replace it with some other thing. Okay, I'll replace it with this one. Okay? I have the same thing. I have the same thing. Okay, ma'am, replace it with this one. Okay. Same thing. No change. Right? So there is no possibility of cis and trans because you are getting the same thing again and again. So there is no GI. GI is not possible. Next is important, that is A4B2. Important and very simple. So you replace one more atom here, right, with this B. So I'm going to replace this. Can you see that? If these two red atoms are opposite, this is trans. Can you see? It is trans, right? It is trans. Can you see that? Now, I'll just keep it on the cis position. Now, can you see that they are next to each other? Can you see that they are next to each other? Can you visualize that? Right? Right? Next to each other, that is cis. Right? So how do we draw it? We draw it like this. When two same are on the same side, that is cis. Wait a minute, it It's actually this one is same, right? We can't predict it from the white one. From white one, we can't predict. White one is also opposite and also next to each other. We can predict this only from this pair, right? That from this pair it is cis, right? And here it is trans, right? So it is definitely possible. M A3B3, very, 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 very important. Very important. Most important geometrical isomerism. Very different also. Here we don't talk about cis and trans. Here we will not talk about cis and trans. We'll talk about facial, meridional. For that you have to understand one thing, okay? So let's understand that. Students, firstly you have to tell me why this octahedral is called as octahedral. Any one of you? Why this octahedral is called? It has 6 bonds. Then why octa? It should be hexahedral. Why it is not hexahedral? Why it is octahedral? Tell me, any one of you who have the answer. Any one of you who have the answer to it. You see this, it has 6 bonds, and now even then why we call it tetrahedral. This is actually my medicine, right? So what I'll do now, I'll try to make a phase out of this, right? So what exactly is this one, right? I'm not able to do that. Just give me a second, guys. Just give me a second. Okay, to make you understand things more clearly, I'll show you why this is octahedral, right? ऐसे ही by doing cramming, nothing is going to work, okay? Cramming is definitely not my way of teaching, right? It is octahedral because it has 8 phases. This is the first triangular phase. Can you see it is forming a triangle? It is the first triangular phase. This is the second triangular phase. This one is the third triangular phase. This one is the fourth triangular phase. Can you see? Above you have 4 triangular phases, right? Then 5th triangular phase, 6th, then this one is 7th, then this one here will be 8th triangular phase. So because it has 8 triangular phases, that's why it is called as octahedral. Because now you know the definition of octahedral, why it is called so, then only you will be able to understand what is facial. It is related to phases, right? So you need to understand what are these phases, right? So in Ma3B3, you will have 3 different atoms. Okay, I'll take 3 green atoms. Okay, so if I draw these 3 atoms on one of the phase, this is on one phase. Can you see that? This is on one phase. Can you see that, guys? If I put this green here, now is this one phase? No, this is not at all becoming one phase, right? This is not at all becoming one phase. If I put this green here, is it becoming one phase? Is it becoming one phase? This is not a phase. A phase, I showed you that these are the phases, 1, either 2, either 3 or 4. So you need to have all the same atoms on the same phase. That is called facial isomerism. Okay, so this is called facial isomerism. Okay, what is meridional isomerism? Simple, very simple. Meridional isomerism is when you have one semicircle. You are forming one semicircle. Can I form one semicircle? One C you can form here, right? Can you see that C? How much simple words, beta? This is the simplest way of teaching you facial and meridional. Facial, beta, triangular, it is forming one triangle. This is second triangle, third triangle, fourth triangle. Total you have 1, 2, 3, 4, 5, 6, 7, and here you have 8. Are you able to understand that why it has 8 phases and what is facial? Facial is when you have all the same atoms on the one face. So these three same atom is on one triangular face. These three same atoms will be on one triangular face. That is called facial isomerism. Okay? Right, everybody? Now, if you talk about, ma'am, what is meridional? It will form a semicircle. These three atoms are forming this semicircle. The C it is forming. If it is over here, here also it is forming this C. Right? This C it is forming. Here also it is forming this C. So that is called as meridional isomerism. Right? Now, ma'am, but this is in 3D. How to understand it in 2D? Ma'am, who will tell us that this is in 2D? How will we will understand this in 2D? Let's understand that. Right? In 2D, let's understand that. In facial, you will have three next to each other, same next to each other. These three are next to each other. That is called facial. In 2D, we will draw it like this. In 3D, you will draw two next to each other, then it will leave one and then you draw one. Okay, similarly, draw two next to each other, leave one and then draw one. That is meridional. Tell me if that is clear to everyone here or not. Tell me, guys, if that is clear to everyone here or not. What is facial? What is meridional? I have told you this in 2D, 3D as well. Right? Then there is, wait a minute, let me see. Till now we have seen MA6, A5, A4, B2. Have we seen A4, B2? We have seen A3, B3. Now we have, before this, no, I have some other also for you. A4BC, right? Let's talk about A4BC. Okay, after this, let's talk about A4BC. A4BC, simple, you have four same, right? Four same, 1, 2, 3, 4 are same, right? Four are same and two are different. A4BC, right? Here, based on this, you will say that this is cis. If you draw it opposite, this will become trans. Right? Okay, this will become trans. We have seen this before also, right? So this is this when you have, wait a minute. This is BC. So this is not A4BC. Okay, now it is. Now if you see how we will draw it, okay? Let's see that. If you see, Let's talk about that. How we will consider that. Okay, let's talk about that. Right? Chal. Now, here also what we will do, this is also one of the exception only. That's why I'm marking it. Okay, I'm marking it in both. Okay, because here what we will see, if these B and C is opposite to each other, we'll take it as trans. Okay, we'll take it as trans. If this B and C is next to each other, then we'll take it as cis. This is an exception. That's why I'm saying we are forcefully taking B and C equal. That's why I have marked it important. Okay. Now, let's talk about, this is done. Then you have A2, B2 and C2. Okay. Let's talk about A2, B2 and C2. I'll just draw it here only. Okay. Let's talk about MA2, B2, C2. This is very, very important and quite complicated also. Okay. So let's see this. Permutation combination we are going to apply here. I'm just teaching you, so that you don't say that, ma'am, you have just given us the answer, ma'am. Why you're not teaching us like properly, ma'am? We are not here to cram, ma'am. Okay, for that I'm teaching you this. Now, see this thing. Permutation, combination, mathematics, you're going to apply this, nothing else, right? So firstly, I'll take, here I'm taking trans pairs, okay? When I'm writing this AA, BB, CC, that means I am saying that A and A is opposite, B and B is opposite, C and C is opposite, okay? So, I'll also take this example here, right? Okay. A and A is opposite, B and B is opposite, C and C is opposite. Okay. So when AA, BB and CC are opposite, there is one geometrical isomerism that you have. Right? Then they are saying, now see, doing this every time we can do that, right? But I'll just tell you with the help of permutation how we can do this, right? Then what you need to do, make pair with each other. It can be AB, then it can be BC, then it can be CA. AB, BC, CA. A pair with B, B pair with C, C pair with A. That is second geometrical isomerism. Then when you fix AA and you interchange these two, this will be BC, this will be BC. Okay. Then you fix BB and you interchange A and C. This will be AC, this will be AC. Then you fix CC and you interchange these two. This will be AB, this will be AB. These are the 5 geometrical isomerism. This is a trick of knowing that how you can actually answer these isomerism. This is like how different. I'll just show you one of them. Like if you want to know, let's say this one you want to know. Let's say I'm saying this is A and this is C. Okay, so it will be AC, A opposite to C, and there is also another one where A is opposite to C. Okay, so here also A is opposite to C and B is opposite to B. So these are the kind of, these 3 isomerism will be this kind. Where let's say if I am saying this is AA, this is A, then AA is of same kind, other 2 are opposite to each other, right? Then if I say this is B, so B and B are of same kind, other 2 are opposite. If I say this white one is C, then C and C are all on the opposite side, other 2 are this one, right? Then you can have A opposite to B, B opposite to C, C opposite to A. All of them are geometrical isomerism, right? So you can say here geometrical isomerism are 5. Okay? You can just write down here that there are 5 geometrical isomerisms. But just similarly, you have this one. Similarly, you have, wait a minute, similarly, you have this one. That is M, A, B, C, D, E, F. Right? So here total geometrical isomerism are 50. Okay? Total geometrical isomerism are 50. Here also you have same kind of pairs, right? I'll tell you how. Firstly, you will have AA. See, here you have AB, CD, EF. Right? Firstly, you will make this one constant, right? Like there are 3 set it will form, then 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 3 set it will form, and 3 into 5 will be 15. So there are multiple combinations here, right? I would not advise you to get into that. Just remember that it has 15 geometrical isomerism, that's it. Okay, right? So it's a like thing of permutation and combinations, right? Okay, here that's why I have showed you where permutation and combination is less. Similarly, you will have to make 15 pairs, right? Okay, so that's how you will have 15 geometrical isomerism here. Now, next one is, wait a minute, AA3 we have done or not? Wait a minute. We have done this AA2B2, right? Then we have AA3, right? Last one will be AA3. So I'm going to write it here only. Then there is MAA3. What you will do with MAA3? 3 ligands, and all the 3 ligands are symmetrical or unsymmetrical? Symmetrical or unsymmetrical? I think I won't be able to make 3 ligands here. You know why? Acha, we will be able to. Okay, thank God. We have these many atoms, thank God. Okay, so these are 3 AA ligands. Bidentate symmetrical ligands. Second, and this one is third one. Okay. Now, if I put this here, you know, now I'm just teaching you geometrical isomerism. I'm teaching you so that you get habitual by seeing these. Actually, you will find usage when you understand optical isomerism. Okay. Okay. Right? You have this. Right? Can you see this? 1, 2, 3. Right? See, you do anything. Right? You replace this with this one, right? Always and always you will have the same thing here. Same thing. That is why there is no geometrical isomerism that is possible here. No matter what interchange you do, you will always have the same thing here. Okay? No matter whatever you do. Right? Okay? So, this is the last category of geometrical isomerism. After that, we are going to start with optical isomerism. Okay, guys? Yes, everybody? Okay, let's see this. MAA2B2. You need to have 2 AA. Okay, I'll have that. And B2. B2 means it is unidentate. Okay, B2 means it is unidentate. So I'll just draw 2 unidentate here. Okay, so I'm just going to draw 2 unidentate. This is bidentate because it is linked. This is unidentate because it is not linked. Right? Now, Here you can see these two are next to each other, right? If I put it like this, if I put it like this, can you see now we are about to form a trans isomer? Can you see we are about to form a trans isomer? Can you see they are opposite? So we have just formed a trans isomer, right? So that means cis and trans is possible here. This is very important, right? So when these two are next to each other, it is cis, it is opposite, that is called as trans. Okay, everybody, is that clear? Okay, okay, yes. Now let's talk about, so this we have done, compounds containing bidentate ligands. This also I think we have done, right? So guys, this is the chart. Remember this chart, okay? Take a screenshot of this chart. If you're not going to revisit the notes or the video, take a screenshot here. This is everything, like you have A2, B, C, D, E is 9, A2, B2, C, D is 6, A2, B2, C2 is 5, A, B, C, D, E, F is 15, right? A3, B2, C is 3, A3, B, C, D is 4. This is very, very important, right? Others don't have any geometrical isomerism. Take a screenshot, very, very important. Okay, yes. Thank you, Ramya. Thank you, thank you. Okay. Will you do chemical bonding detail like this? I'll do that. After periodic classification, I'll do chemical bonding only. Okay? Yes. So that is done, right? That is done. Take a screenshot of this one as well, right? This is the table that you should remember. Everything else I just taught you just to teach you that how this happened, right? So that even if you forget that in the exam, you can do it yourself, right? Otherwise, remember this and this. Okay? Now, let's do this JEE 2023 question that says, consider the following reaction and statements. This is the reaction and statement. So he is saying that two isomers are produced if the reactant complex ion is a cis isomer. Okay. See, if I take reactant as a cis isomer, it will be like this. It will be, this will be Br, this will be Br, this will be NH3, 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 NH3. Okay. Then if you replace this with the if you replace one Br with NH3, either this Br you will replace, it will form this kind of situation, or this Br you will replace, or this Br you will replace, right? So two isomers will be formed, are produced if you have the reactant complex is a cis isomer. Two isomers are produced if the reactant complex is a trans isomer. Okay. Only one isomer is produced if the reactant complex is a trans isomer. Only one is a trans isomer or a cis isomer. Okay. So for that you should know one thing. Okay. So if you draw this here, actually 1 and 3 are correct. So I'll tell you how. Okay. So if you see this, if you have a cis isomer, right, like this, and you're replacing, like you're replacing one NH3 with Br, right? So what are the two possibilities you can have? Either you can have, okay, I'll just draw. In fact, you know, for this particular question, I should not use 2D. I should use 3D to explain you this, right? Answer will be 1 and 3. Let's see how. See this thing, okay? This is very important question. Now, what you had here, you had NH4, right? 1, 2, 3, and 4. If it is a cis, 1, 2, 3, 4, cis means they both are next to each other. Okay? If I replace one cis, one of this is NH3, these all are Br. Okay? If I replace this one, then what will happen? Right? So I can have this kind of situation. Right? Wait a minute. I am replacing one of the NH3 with Br, right? So wait a minute. So I have this situation now, right? Now I need to replace one white atom with green atom. That means one NH3 with Br. Two possibilities are there. Let's see how. Okay. First possibility is that you replace this white atom and you have this kind of semicircle. That is nothing but meridional isomer, right? Another possibility was that you had this cis isomer, right? And you replace it over here. If you replace it over here, it will form a facial isomer that is on one face. That's why here it's a very, very important question. Then it will have one facial and one meridional isomer. Very important. Very important. Right? Now for trans, there is no such thing as facial and or meridional that it is going to form. How? If you see this here, right, this is your trans isomer. Okay? You replace, right, maybe you're replacing it here, you are making a meridional isomer. You are replacing it here, you are making a meridional isomer, right? If you are replacing it, let's say here, again you are making a meridional isomer. So there is no possibility of facial isomer, right? So always you have only one isomer that you form, that is meridional. Very, 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 very important question. No matter how much important I mark, this is a very important question. Okay, so 1 and 3 is the correct statement. So answer will be C. Now let's talk about optical isomers. Okay, let's talk about let's talk about optical isomers. Guys, just give me 2 minutes, right? Okay, just give me 2 minutes. I'll be back in 2 minutes, right? After that, I'm going to start with optical isomers. Okay, yes. Students, I'm back. Yes, everybody. Okay, let me see. I think there is some thing. It is being cancelled. I think now it's fine. Okay. Now we are going to talk about optical isomerism. Okay. Optical isomerism. So first you need to understand what is optically active, what is optically inactive, what is plane of symmetry, everything. Right? Okay? Yes. For that, let's talk about one thing. If you talk about optically active compound, optically inactive compound, if you talk about the experimental perspective, what happens? You have a plain unpolarized light that is in all the directions, okay? Then you pass it through a Nicol prism, right? Then you will have a plain polarized light. Now, this plain polarized light is passed through a compound. It is passed through a compound. There are three possibilities that can happen here. It is passed through a compound. Okay, it is passed through a compound. Three possibilities can arise out of it. First, second, and third. First possibility is that this plane polarized light will rotate. Okay, it will rotate towards the right side. Okay. Second possibility is it will rotate towards the left side. Third possibility is there is no rotation. So when there is no rotation, that is called as optically inactive. And these two are optically active. Optically active. But you have, when it is on the right side, that is called as dextro. That is represented by small d. When it is on the left side, it is called as levo. That is represented by L. That is represented by levo. That is represented by L. But now the next thing is, ma'am, you have given us a compound. We can't always like experiment this, right? We don't in our exam. How you will find out? You don't have experimental apparatus in the exam, right? So how you will find out this is dextro or levo, right? Now in coordination compound, you don't even have to find out it's dextro or levo. You just have to tell whether it's optically active or it's optically inactive. That's it, right? Optically active or inactive. That's it. So how you will tell that? So always remember that these are non-superimposable. If something is optically active, it is non-superimposable mirror image. That means image means it has absence of US. Simple funda. If you have plane of symmetry is not present, it means it is non-superimposable. Non-superimposable, imposable mirror image. And this means that it has POS is not present, so non-superimposable mirror image, and you can say it is optically active. So in all the compounds, we'll be trying to find out the plane of symmetry. If plane of symmetry is present, optically active, it will not be. Okay, if POS is absent, it will be optically active. That's it. That's the only thing that we're going to do in next 30 minutes. Okay? Yes, everybody? Got it? Achha, now the question is, ma'am, what is this plane of symmetry? What is this plane of symmetry? This is my hand. This is my hand. If you draw a mirror here, if this is my hand, if I draw a mirror here, I will get this kind of situation. So they both are non-superimposable. If I have this mobile, okay, wait a minute, this I have, right? Now, if I draw a mirror image, you will get the same thing, right? So that's why it is the superimposable mirror image of each other. Like if you say you have X, and why always you take X, ma'am? Why can't you take A, B, C, D, E, F, right? Because I want to remind you something, right? Someone will come in your life, they will become X. But when you study, right, you become something in life, you have good career, that will never become your X, right? X will try to come back when you have good career, right? So this is X, right? If you take a mirror image here, this is going to form the mirror image that is superimposable. So this is a superimposable mirror image, right? And we are looking for non-superimposable mirror image with no plane of symmetry, right? Okay, yes, everyone, let me know if that is clear to everyone here. Okay, let's understand this. We have already done. Okay, this also we'll talk about, okay, later on. So firstly, let's understand tetrahedral. Tetrahedral, actually, before that, let's understand square planar, okay? Let's understand square planar. That would be a better way of understanding this, right? Wait a minute. I think now it's better. Yes. Okay, sure. Now, one very important thing is, if you talk about coordination number 4, tetrahedral is not going to show you geometrical isomerism, but square planar is not going to show you the optical isomerism. Can you tell me why? Any reason? Ma'am, why you have done this? Why it is never going to show any optical isomerism? See, simple thing is, ma'am, let's take all of them different. Okay, I'll take all of them different. Okay, I'll take one green atom, one brown atom, one gray atom, and I'll take one purple atom. Okay, ma'am, how it has plane of symmetry? There is one plane that will pass like this. It will cut this atom into half, this atom into half, this atom into half, and this atom into half. That plane is going to cut every single thing into half, right? And that plane will always be present. See, if you talk about, ma'am, A2, B2, A4, A3B, it may have more than one plane of symmetry. I am taking the worst case possible. You have all of them same, right? All of them different. Even then there is plane of symmetry. This plane of symmetry is always present. So it is never going to show any geometrical any optical isomerism, right? Square planar never shows optical. I know you guys are so happy. You're like, ma'am, thank God. I wish, ma'am, tetrahedral and octahedral also don't show any optical isomerism. I mean, it will become so easy. But I'm so sorry, tetrahedral and octahedral, they will show. But you know, the good part is very rare will show. Most of them will not show, right? So that's the best part, right? So let's understand this, right? Okay. Let's understand this. So here you have MA4. I'm going to talk about tetrahedral geometry, how it looks like. See, simple is, if all of them are same, beta, all of them are same, it's not even a question. I know in your head you're like, ma'am, easy, ma'am. Any plane, you take out this plane, okay? I'm slicing it like this. You have to imagine this, okay? In optical isomerism, there is a lot of imagination that is needed. This structure I have given you, most of the work I have done. Now you just have to imagine a knife that is slicing this. When it will slice this, this will be into two parts, this atom will be in two parts, this will be in two parts. And it will slice up into two parts which will be same, two equal halves. If it is slicing them into equal half, that means plane of symmetry is the present, right? Plane of symmetry is present. So we can say POS is present, optical isomer will not be present. Okay? Right, everybody? Right, everybody? Now I'm going to just, what is happening? This is like moving here and there. Atoms are highly unstable. Huh? Okay. Now, you know what I'm going to do? I'm going to do one thing here. I'm going to write it on one page only, okay? I'm going to write it in one page only. On this page, I'm going to write all the isomers, okay? Because most of them will not be possible. I think this was a good one. Huh? Let's draw it here. Let's write MA4. As you can see, POS is present, so optical isomerism will not exist. Then we have Then we have MA3B. MA3B or MB3A. Whatever you have, that is the same thing. That means you will have three atoms which are same and one atom will be different. Students, when you visualize this in reality, this will become very easy for you. This becomes highly easy. You can see the structure. Now you will see, ma'am, this is not at all a big deal, right? You have this, you slice them, this green atom. If you see it like this, then you will say, ma'am, POS is not present. Here you will say, ma'am, POS is not present. Like this, POS is not, no, like this also it is present. You slice this will be half, this will be half. This and this will be on the opposite sides, right? So we can easily slice them up into equal half. So POS is definitely present, right? So you can say optical isomerism will not exist. Third one is you have Ma2B2. Okay, Ma2B2. So now you should have two atoms which are same. Okay. Now two atoms which are same. If you see it like this, you will say, ma'am, no POS is present. If you see it like this, ma'am, no POS is present. But if you see it like this, yes, you slice this, or you can also take it like this. You slice this, it will cut into equal half. Can you see that? It will be cut into equal half. If you see it like this, it will cut into equal half. If you see it like this, it will cut into equal half. So there is definitely POS present. Optical isomerism does not exist. Next is you have A2B2, AB2. Okay. Achha, before AB2, I want to teach you ABCD. Yes, this one is interesting. Okay, and actually simple also. All of them are different. Okay, now tell me whether POS is present or not. Uh, okay, now tell me POS, this will be cut into equal half, this will cut into equal half, but this and this are two different atoms, so no equal half. You place it like this and this are two different atoms. You place it like this, no. 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 You place it like this, not possible. You place it like this, not possible, not possible, not possible, not possible. There is no plane of symmetry. You do everything. There is no plane of symmetry, right? If you keep this in the at the top, if you complete this at the top, if you keep this at the top, keep this at the top, there is no POS present anywhere. So you can say POS is not present. So here optical isomerism, you know what I'll do? I'll rather write it here, right? MABCD, very important. POS is not present, so optical isomerism will exist. Mark it important because till now this is the only tetrahedral where we have observed optical isomerism, right? Okay, right. Any problem, any problem, any problem, right? Okay, any problem. Yes. Now, let's talk about when you have bidentate, unidentate ligands, okay? Let's talk about when you have bidentate, unidentate ligands. Tell me, without these structures, will you find it difficult if I don't show you these structures? If I don't show, you will not be able to understand only that, ma'am, what you are saying, which POS, how it will cut, how it will not cut. You know, when it will become more complicated, but for you it will become easy. That's my guarantee to you, right? For you it will become easy, right? Okay. Now, if you see this here, this one is, if I see optical isomerism, right? Now, this one is for M. Let's talk about M. If you have AA twice, that means you have two bidentate ligand of same thing, right? Arey yaar. Why these atoms are on that having too much kinetic energy moving here and there? This is a unidentate ligand. This is a unidentate ligand. Students mostly find bidentate ligand tough, right? So these are not unidentate, these are bidentate ligands, okay? So if you see, can you pass a plane of symmetry here? Tell me. Can you pass a plane of symmetry here? See, if I see it like this, can you see this? Can you see this? Okay, now can you see this? Now is it better? Now, I'll just reverse this. It's nothing but two. One bidentate ligand is here and other is here. Okay, so I'll just put it like this. Okay, or if you want to see it like this, that is also easy. One bidentate ligand, one. If I pass a plane like this, it will slice this full bidentate into equal half, and this part will be divided into equal half, right? So definitely plane of symmetry is present. Bidentate ligand, like what kind of bidentate ligand? Bidentate ligand like NH2. Bidentate ligand like CH2, CH2, NH2, NH2. You will, if I am drawing this kind of bidentate ligand, that is CH2, which is symmetrical, right? So if I am slicing this thing, that means this NH3 here, this all atoms are getting divided into half. This means I am actually splitting this thing into half. So that is also equal half, right? So you can say that POS is definitely present here. POS is definitely present here. So optical isomerism will not exist. Okay. Next is you have AA and BB. You have AA and BB. See how you're going to teach. How you're going to teach, I'm saying how I'm going to learn. Okay. This is AA and BB. Okay. That's how you have AA and BB. Okay. Now, again, same thing. You slice this, right? Take a knife and slice this cake cutting. Okay. When you cut this cake, this will be divided into equal half. Okay, I'll show you like this. Okay. You are cake cutting, you slice this will be cut into equal half. And this here, the one that you have in front, that will be cut into equal half. So can you say POS is present? Yes, ma'am, definitely. POS is present. Optical isomerism not possible. Right? Third one is you have done AA, BB, you have done. Then let's do M of AA and then you have AB. Okay. Now you are going to have two. You are going to have one AA. Okay. Usually we are representing red one with A, so I'll represent that only. And here you will have one B. So what I'll do, I'll just replace it with one atom. So this is going to be AB. Okay. See if optical isomerism is present. Is it present, everybody? Let me know, is it present or not? Is it present? If you slice this, passing a plane here, this will be cut into, this atom will be half. This atom will be half. Basically, I am saying that this is an atom, you cut it into equal half. This is what we are doing here. Okay, so this atom half. And in the front, what you have, that is same only. So that will be one red atom here and one red part here. So that is also equal half, right? So can I say here also POS is present? Optical isomerism does not exist. Last one is M of AB2, right? AB2, you need to have two atoms which will have, now this one is very interesting. Okay. This one is interesting. Okay. Earlier what we were doing this thing. We were always passing a plane here which will cut these two into equal half. Then in the front you will pass into equal half. But earlier you always had two same, like that was a symmetrical ligand. So always it was cut into equal half. Now this is unsymmetrical ligand, like you have glycinate. Now if you pass a plane from here, if I pass a plane from here, this will be cut into equal half. But this will not be cut into equal half. Any other possibility? If I take this as a possibility, definitely not possible. Other possibilities are not there. If I cut this into equal half, this will be cut into equal half. But this one, not possible. So that means POS is not present here. right? So you can say POS is not present. In fact, you should write it with some different pen, because here you have find out that POS is not present, optical isomerism exists. And this, till now, this is the second case where we have seen optical isomerism present in the tetrahedral complexes. So this was the first one and this was the second case, right? Okay, first case and second case. Tell me if that is clear. Hmm. Tell me if that is clear. Okay, everybody, any problem? Because the last part we are going to do optical isomerism in octahedral complexes. Okay. Everyone, spam the chat box with green hearts if you genuinely feel that this lecture is giving you something beneficial, right? If you genuinely feel that with this lecture you're learning something, right? If you feel that I have put some efforts for you here, right? If you feel that, then spam the chat box with green hearts, right? Okay? Yes. Very good. Very good. Okay, let's see octahedral complexes. Let me just draw that. Same way we are going to do that. Same way. Only future iodine is dropping the green hearts. What about others, huh? And have you liked the session or not? Or ma'am is putting the efforts, but you guys are doing nothing, huh? Over there. Let me see. Very few likes. Very few likes. Till now, it should have crossed around 70 plus. Right? Very bad. Huh? Very bad. Those who are watching it on the recorded version, do like, share this session, write it down in the comment section how you're finding these sessions, right? Because that makes us also very happy, right? Just imagine you are cracking like your AIR 1 and still not getting any college. Same thing, right? So let's understand optical isomerism. Where we were. Acha, acha, okay, fine. Now, guys, I'm giving my throat, my tonsils some rest, as you all know, right? Let's see this, right? Let's see this, right? Okay, yes. But you yourself are better evaluator for that. Just understand this is the level that we are teaching you in free of cost. So if we charge you something, then what level we will provide you? Just think about that, right? Okay. So definitely Sigma is always better than YouTube, right? Reason being because other things apart from the content like mock tests, touch modules, right? Then your DPPs, practice sessions, doubt sessions, right? Everything is provided there, right? So, and in there also, if I want to teach isomerism, I'll teach that in 3-4 lectures, right? Rather than just one lecture, right? It's content will be same. It's just that more question practice will be there, that doubt solving will be there, these things will be there, right? So let's see this, right? 1, 2, and I think 3 pages are enough for that, right? So first is I'm going to draw M6, MA6. So if you see MA6 here, this is the kind of structure that we are drawing here, right? This is the kind of structure that we are drawing here, right? Can you see that, everyone? Can you see that? Yes. Is there any plane of symmetry? 1, 2, 3. Three plane of symmetry. Okay, you can pass it from here, you can pass it from here, you can pass it from here. So many plane of symmetries you have. So definitely POS is present. Optical isomerism will not exist. Then you have MA5, A5B. Okay. Now students, here what you will have, A5 means 5 atoms will be on the same, 5 atoms will be same, 1 atom will be different. Okay, 1 atom will be different. Now if I pass a plane like this, if I slice, this is the knife, you want to cut your cake, right? That's the cake you want to cut, you want to slice it up. This you will slice, and this atom will cut into equal half, this will be into equal half, this on the back side will be into equal half, and these atoms will be on 2 different parts. So it can be cut into equal halves. You can say POS is present, optical isomerism does not exist. MA4, B2. B2 means this thing. Now, Bacha, this is very important, okay? This is very important. Because here you have cis and trans both. Okay? Okay? I think it was given here as well. Let me see. It's not given here. So I'll draw it, okay? I'll draw it. This now, I would advise you to write here coordination number 6. Okay? I would like to draw it here, right? Because here it will exist. Okay, see, simple thing is one possibility is trans. So you'll draw one possibility as trans. This is, let's say, B and B. This is A. See, in trans isomerism, definitely you can cut into 2 equal halves. You can cut it into 2 equal halves. Possibility is there, right? So in trans, POS is present, so optical isomerism will not exist. Let's talk about cis. 2 are next to each other. This is A, and this is cis. If you talk about cis, in this case, what will happen? This will be next to each other. So, can you see, is there any possibility here? Is there any possibility? This is the plane of symmetry. Can you see this? If you pass it from here, this will cut into equal half, this will cut into equal half. Others are same only. So, definitely POS is present here. So, can I say that here also POS is present, so optical isomerism will not exist. Okay? Optical isomerism will not exist. Now, next one is MA4BC. Okay? Same it is. Even if you pass BC like this, right? It will cut into equal half, even if you have them opposite. Right? Even if you have them opposite, then also it can be cut into equal half. Both possibilities, it will be cancelled, cut into equal half. So you can say POS is always present, whether it's cis or trans, so POS is always present, right? And optical isomerism does not exist. Next is A3B3. A3, B3 were of two types, right? What were those two types? One was meridional, one was optical. Sorry, one was the meridional, one was facial. So this was meridional. Meridional, you can pass plane of symmetry, right? Here you can pass plane of symmetry, right? It is possible, right? Then facial is like this. Oh, wait a minute. Facial, facial, facial. It will be like this on one face. Can you see? This is one face. Here I doubt it. Wait a minute. Wait a minute. A3, B3, no? A3, B3. Wait a minute. MA3, B3. It is also of two types, meridional and facial. Okay. Wait a minute. This is very important, okay? In this case, in meridional, POS does not exist. Sorry, POS exists. So optical isomer was there. Sorry, optical isomer was not there. But in facial, if you see, this is one face. There is no possibility of POS, right? If I pass the plane from this side, then this green and this white are not equal. If I pass a plane from this side, wait a minute, there is possibility. Wait. Then, if I pass the plane like this will cut into equal half, this will cut into equal half, these are equal, these are equal. Yes, POS is present here as well, right? Okay, so POS is present here, guys. Optical isomerism here also does not exist. Okay, POS is present here. It is cutting it into equal half. If you see this here, this white and this green will be cut into equal half. This green and green are two parts. White and white will be two parts. So that means POS is definitely present like this. Like this it is present. There is no other POS that is present. Only this POS passing from here. Like this particular sheet. Right? If I talk about the plane should be passing like this. Okay? So I'll give you a plane. The plane should pass like this. Okay? Can you see? That is equal half. Okay? Can you see that in 3D? That is equal half. Okay? Now I am showing you my pen tab as the example. Right? So that is dividing it into equal half. Okay? Now, next is, wait a minute. This we have done. A4, BC, have we done that? A3, B3, we have done that. Then A2, B2. A2, B2, C2. Okay? A2, B2, C2. Let's talk about that. A2, B2, C2. A2, B2, C2. So we need two different atoms here. Right? A2, B2, C2. See, here you will find very difficult to have plane of symmetry. Right? A2, B2, C2. If you pass the plane from this side, these two are different. Okay? See, simple is, if I pass a plane like this, we know that this blue and this green one is different. Okay? Can you see that? I think from camera it is more clear. Right? From the camera side it should be more clear. Right? I hope so you are able to see that. Right? So even if you pass it like this, then also it will be same. Two are different. If you pass it like this, let's say like this, even then it is different. If you pass it like this, even then they are different. Right? So that means there is no plane which is present. right? Now, what about MA3B2C? MA3B2C. Wait a minute, we'll see that. We'll see that if I have not included that, then we will see. Okay? If you have asked something, I'll tell you that, right? So here POS is not present, so optical isomerism exists. Can I say A2B2C2 optical isomerism exists? And I would advise you to mark it in red because optical isomerism is existing here. Okay, mark it important. Then last one is this you have seen. Then you have MABCDEF. Before that, one student is asking me, ma'am, MA3B2C. Okay. MA3B2C. Chalo. MA3B2C. MA3 3 should be same. Then you have A3B2C. Here also, no, if you see, if I have this kind of structure, if I put it like this, if I have a trans of, simple thing is, if I have a trans of this, okay, these two are opposite. This is trans, okay. If I have a trans of this, POS is present here. You can see you pass a plane of symmetry, it is dividing it into equal half. So POS is present in trans. So you can say in trans, POS is present. You can say in trans, POS is present, optical isomerism will not exist. In case of cis, when they are next to each other, right? In that case, is there any possibility? Let me see. Yes, in case of cis also you have a possibility, okay? In case of cis also you have this possibility. Cis means they are next to each other. You have this possibility. That means cis also POS is present. Optical isomerism will not exist. Okay, now let's do the last one, A, B, C, D, E, F. This one is actually very important, right? So I would rather write it on the next page. Okay, I'll rather write it on the next page. Do you remember I gave you this, how many geometrical isomerism it was having? A, B, C, D, E, F. How many of you remember? It had 15 geometrical isomerism. Okay, it had this. You have to beta cram only because otherwise permutation combinations are very weird. You will find it, you will get confused. This is 15. And every single geometrical isomerism is forming an optical isomerism. So each 15 are forming optical isomerism. So that means this is a very important thing. Optical isomerism will be total 30 because in optical isomerism, right, where it is existing, when I say here optical isomer exists, I say two optical isomers because one is the GI itself and other is the mirror image. These are the two optical isomers. If I say here it exists, here to nowhere it is existing, right? If I see this here, each GI is forming one non-superimposable mirror image. Some teachers will not teach you this. They will directly tell you that this does not exist and this exists. Okay. That is also a good thing that you don't that you don't know anything, which you don't know, how you will get confused. But my idea is that you should know. If they ask you in the exam, like, what if they confuse you by asking you this or this or this? You should know that this does not exist. That's it, right? Okay. So now, if they ask you total stereoisomers, students, you know what they do? They do 30 plus 15, ma'am, 45. This is a wrong method, right? This is the wrong method. This one reel is getting very famous on Instagram. This is the wrong number. So this is the wrong number. Okay. How many stereoisomers you have? 15. And each 15 is forming one mirror, superimposable mirror image. So total optical isomerism are GI plus 15, that is 30. And total stereoisomerism is this divided by 2, that is nothing but 30 only. Because this 30 already has the GI. Okay, this 30 already has the GI. It's the same thing. Okay, let's say there are 5 friends. You have 5 friends. Okay, 5 friends. 5 friends, 1, 2, 3, 4, 5. All of them have, all of them are committed, right? Now you can't say 5 friends, right, when they were single, right? Now they are committed, now total there are 15 persons. No. Here they are single, like GI. Here they are committed, they have pair, right? So out of these 10 people, 5 friends you have already included here, right? Okay. But don't do that. Frankly, don't do that, right? You will get confused only. It's simple thing. Let's not complicate it, right? Permutation, combination, and you have to make sets here, right? I'm not saying that. I know you are thinking that, ma'am, we know permutation, combination, we can apply that, right? But let's not apply math here, okay? Sure. Now, this is done, EE. Now, I'll ask you 2, 3 more questions. This we have done, AA3, then you have AA, B2C2, then you have AA2B2, okay? So, first is MAA3. Let me see if you have all of this. I think we have already one AA3. Then this is the example. Then AA2B2. This we have written here. Then we have AAB2. Okay, chalo, I'll make this for AAB2. Okay. So first is AA thrice. Okay. This means what you have is you have 3 ligands, guys. This is very, very important for you to understand. Okay. This is very important here. Most of the students say that POS will be present, but POS is not present here. Okay. I'm also telling you that what most of the students will say. I'm also telling you that what is not the reality. Okay. See. This is genuinely very, very interesting. I'm just making AA3 here, right? I know you might feel that, ma'am, POS is present. How many of you are thinking POS is present? This is plane. If I pass a plane here, what you are looking at is just red atoms. You are saying, ma'am, these all are sliced up. Ma'am, this is, and this is the thing that you are left with. That is same. This is red, this is red. No, these are linked. Here it is linked with this one, here it is linked with this one. The axis will change. When you pass a plane from here, right, what you will have is this particular ligand will be cut into half, but here this is, for example, on the x-axis and this is, for example, on the z-axis. So the axis has changed. So it is not divided into equal half, because here what will happen, along the y-axis You will have something that is on the z-axis. Here you will have along the y-axis something on the x-axis. That means what you have is you have a pair of, if I divide this, you will have a pair of y-axis with this x-axis. This half ligand will be paired up with this x-axis. And you will have this y-axis, this particular ligand, half of this with this z-axis. So they are definitely not same, right? Okay. So this is a simpler way of teaching you that how it is not the same. Tell me if you are able to understand, otherwise I'll draw the diagram. Right? If you're not able to understand, I'll draw the diagram. This actually forms. Now you might feel that this is 1, 2, 3. Ma'am, how come they are not forming any plane of symmetry? If you draw the mirror image, now some students think that, ma'am, we can rotate it. Okay, you can rotate it. Let's say this is x, this is y, this is z. Okay, I'll just make a new page here. Right? Let's say this is the thing. Okay. This is AA, AA. When you see the mirror image here, I'm in 2D, I'm explaining you, okay? Mirror image means this will become AA, this will become AA, this will become AA, right? This is the mirror image. Okay, this is the mirror image. See one thing. Easiest way I'm explaining you, right? It is x-axis, so this opposite, this will be x. This was y, then this will also be y. This is z, then this will also be z. Rotate it now. You are saying, ma'am, I am doing the rotation. Because after rotation, ma'am, see, after rotation also it should be same. Mirror, if I say it is a non-superimposable mirror image, then it should be non-superimposable even after rotating. After rotating, what I have here is this one. I am rotating. If I rotate this at 180 degrees, what I have is this will be rotated to this side and this will be your x. Okay. This will become x. If I rotate it to this one. If I rotate this, then this will become y. If I rotate this to 180, this will become opposite. That means this will come to this side. That means this particular thing will become your y. This is rotated to 180 degree, it will become opposite. So 180 degree rotation means opposite. So this will become z. How they are same? X's are not same. This earlier is on x-axis, this is on y-axis, this is on y-axis, this is on z-axis. So even in 2D, you can see that this is not coming out to be same. So they are non-superimposable mirror images. I have also taught you in 2D, in 3D also I have taught you that if you pass a plane here, this is, let's say, the y-axis. This y-axis is with this one, that is z-axis on one part. This y-axis is with this one, that is x-axis on another part. So how come they are same? Not same, right? Okay. Okay, Ji. So that's why they are of two types, levo and dextro. Okay, that means we can say optical isomerism exists. Plane of symmetry is not present, optical isomerism exists. Then there is one more, that is for M. Last two we are left with, okay? Last two. MAAB2C2. MAAB2C2. AA means it is a bidentate ligand, okay? So AA you have, then you have B2, 2B you have, two different B you have, okay? Then two different C you will have. Two different C you will have, okay? So tell me if now optical isomerism is present. See, if I want to see the trans of it, see this is the cis, where these two are next to each other, these two are next to each other, these two are next to each other. So here I have drawn the cis part. Two parts are possible here. Two parts are possible here. One is cis and other is trans. One is cis and the other is trans. Cis and trans. In cis, you can see that no matter how much I try to pass the plane, there will always be something that is different. These two are different. If I pass it like this, these two are definitely not possible. If I pass it like this, these two are different. If I pass it like this, definitely not possible. So that means always it is going to show us no plane of symmetry. Optical isomerism always exists, and that's why this is very important. That in cis, it shows optical isomerism. In trans, let us see that. In trans, let us see that. In trans, it will be opposite. Can I have anything opposite here? Wait a minute. Let me see. We can draw. Actually, not possible. Trans, possible. Yes, possible. Trans is possible like this. Okay. Trans is possible like this. Now, is it possible? Yes. You draw a plane of symmetry here. Pass of this will be cut into equal half. These two green atoms, if I pass a plane from here, these will be cut into equal half. These will be cut into equal half. And this is same. So I can say definitely POS is present here. So POS is present, and that's why optical isomerism does not exist. Last one of today, that is when you have AA2 and B2. Okay? 2 AA you have and one is B2. Apart from this, they are not going to ask you anything. That's my promise to you. Okay? AA to B2. Right? Everybody, who will tell me if there is any possibility or not? If you draw the cis, this is nothing but this is cis. Can you see they are next to each other? In cis, if you pass a plane here, not possible. You will see, ma'am, possible, ma'am. This is red, this is red. But guys, can you see? This is bidentate, this is bidentate. If you pass a plane from here, right, you are going to again get stuck in that. This is, let's say, along x-axis. This is, let's say, along y-axis. Axes are different. This is this one axis and this is this one. This is this axis. This is this axis. Axes are different here. That's why you can't pass the plane from here. So in cis form, it is possible. Cis form is optically active. Trans form here, if you want to see the trans form here, okay. Transform will be like this. Can you see? Directly we can see you pass a plane from here, right? directly it is divided into equal half. There is no problem with the x's as well. They both are on the same axis. This is on the same axis, right? So you can pass a plane, cut it into equal half. So can I say that POS is present, optical isomerism does not? So in that case, we have written that this one only in cis form optical isomerism exists, because POS is present, POS is, sorry, absent, so optical isomerism will exist. This is how D and L optical isomerism will exist here. Okay? Understood, everybody? I hope that is clear to all of you. Now there is only one thing that we are left with, and can you tell me what is that thing? Only one thing that we are left with. The thing that you were waiting for. Trick, ma'am. Please give us some trick. Okay? So this trick is applicable in most of the cases. I am not saying always, right? But in most of the cases, this trick will be applicable. Okay? Most of the cases. Let's see that. Trick says that a compound will be optically inactive if first point is it has this kind of pair A, B, B, right? Same type of trans pair is same ligand. Or you can say if you have at least one trans pair with same ligand. At least like you have one AA or BB or CC, that will be optically inactive. Okay. Then you have more than one same pair. This is most of the cases this will be applicable. More than one same pair. For example, you have, let's say, M, AB, AB, CC. This is, I'm drawing the trans pair. I'm not drawing bidentate ligand. I'm drawing the trans pair. All are here unidentate. Okay. I am talking about unidentate here. I am not talking about bidentate. I am talking about unidentate. This is a trick. Okay. Now, because these two are same, actually this will be written as like this. M, A2, B2, C2. So if you have any pair, any geometrical isomer where these two, and here I am talking about actually geometrical isomer, right? If in geometrical isomer you have two same trans pairs, then it will be optically inactive. Okay? Okay, G. Very good. Right? Now, this is a question. Let me see how many questions you have. We have only one question. We have two questions exactly here. This we have done, no? This we have done. Okay? Yes. Okay. Firstly, I want to show you the tables here, right? This is the first table that you should remember. Second table that you should remember, geometrical isomers, optical isomer, everything is written here. Okay? Table, everything, geometrical, optical, everything. Enantiomers are nothing but optical isomers only. Right? Now let's solve some questions. This will also be your homework. Okay? This is also going to be your homework because this is very simple. I have already done this. Right? Okay? Now let's do two questions here. First is, you have a homoleptic octahedral complex having all the same ligands formed using, this is 2025 question, monodentate ligands will not show stereoisomerism. See, homoleptic means MA6. Will it show stereoisomerism? Will it show geometrical isomerism? It will not show. Will it show optical isomerism? No. So this is correct. Right? Cis and trans platin are heteroleptic complexes of PD. See, what is cis and trans platinum? If you see, cis trans platinum is anti-cancer agent, right? Cis platin is NH3, NH3, Cl on the same side. PT, NH3 twice, Cl twice, that is cisplatin, and this is your anti-cancer agent. And that is definitely heteroleptic. So you will say this are heteroleptic complexes of PT, cis and trans platin are heteroleptic. Yes. Okay, so both the statements are correct. Right? Wait a minute. Cis trans platin are heteroleptic complexes of PD. Yes. Then why statement 1 true is false? No, both will be true. Cis trans platin are heteroleptic complex. Acha, PD it is written. PT it is na. Yes. PD it is written. So it should be PT. So that's why answer will be that this one is, second statement is false. Okay. Right. Then the next question is, correct statement on the isomerism associated with the following complexes, right? So this is nothing but Ma5B complex. This is Ma4B2 complex. This is Ma3B3 complex, and they are asking you the isomerism associated with this. Geometrical and that you have to tell. So each of them you can tell. For A, you can tell. But directly I'll tell you the chalo, let's see this, okay? A5B. See, if you talk about A5B, so definitely it was not showing us any geometrical isomerism. GI it was not showing. And optical isomerism, POS was present, so optical isomerism also it was not showing. A4, cis and trans it was showing, so GI was present. And optical isomerism, if you talk about cis, right, 1, 2, 3, 4, 5, 6, if you talk about this A and A, this is B, 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 this POS will pass, right? If you talk about this B here, this is also B, and this is A and A. In this also, this one is, you can easily pass the POS here as well. Right? So you have to imagine that, okay? So optical isomerism will not be present. A3, B3 was showing us geometrical isomerism by facial and meridional, and both were not showing us optical isomerism. Right? So we have done this. We will say that AB show GI, AB show GI, no, B and C shows GI. B and C show GI. B and C shows only geometrical isomerism, that is the true statement. AB show GI, no. Optical isomerism, none of them are shown. So D is the correct answer. Okay, you have to imagine that, right? If you're not able to imagine, go through the lecture again, right? So in front of you only, I have imagined. That's the reason I have not picked up the structure. Because once you know the structure, you can imagine that, okay, just close your eyes and imagine the bonds and try to cut it. Okay, so power of imagination is only possible if you have seen those structures, right? Now guys, this is the table that I have already shown you, right? These are the tables. Check for optical isomerism, calculate stereo isomerism for Ma3BCD. This is your homework. First question. Second is, in coordination compound, the hydrate isomerism differ in which of the following? This is the second question. Third is, the complex that can show facial meridional isomerism, which one? This is the third question that you have. Let's see, at least 2 questions you have to attempt. Okay? Right? Very good. Okay, so guys, that's it for today. Now, can you tell me what is this? Is this non-superimposable or this is superimposable? Is this non-superimposable? If you place this picture here, that is non-superimposable. Non-superimposable. Right? Okay. So, this is L Jackson. This is D Jackson. Isn't it? So, that is going to be levo on the left side, and this should be small l and small d, right? Okay, if you are talking about that, right? And that's it. This is our Telegram channel where all our informations regarding our lectures will be there. Now, I want you guys to write it in the chat box. What is isomerism? That is nothing but, have you listened to that same? Same, but different. Same, but different. So this is same, but different, right? That's why you're like, oh my God, I'm getting confused. Because same, but different, right? So write it down in the chat box, same, but different. And also write down your homework in the comment section. Okay? Yes, everybody. Is that clear? Thank you so much, Shanmukha, Future IITian, and Naseem. Thank you so much. Now, guys, very important information as you have asked for this also, right? Wait a minute. Why I am not able to see that? Huh. So, oh my God, very good, very good. Thank you so much, guys, for so much love, right? And also do like the session. Huh? I see you guys don't like the session, right? Don't forget to hit the like button here, right? Okay. So, if you see this over here, here you will see Sigma JEE 2026, right? And that is your, click on this one. Now, this Sigma batch, one of the students was asking me that, ma'am, Sigma batch is better or YouTube is better? See, definitely on YouTube, we like give best content, right? But if we are providing this for free of cost, what we will provide if we charge something from you? That is the first question you ask yourself, right? Second question. See, on YouTube, there are so many distractions that are not there in the Sigma batch. There are leaderboards, there are quizzes on daily basis. Fixed slots are there, right? Not only 2 classes, we have 3 classes daily, right? It is the evening slot only. Moreover, right, you have mock test. Now, tomorrow I'm saying this Saturday, students have their mock test. There is JEE mains and JEE advanced mock test also for JEE students, right? Then not only this, we provide you Tattva modules, we provide you DPPs, we provide you Tattva modules are basically practice questions. Then students, we provide you these QR cards, right? As you can see, these will be delivered at your home, right? These are the short revision cards that you need, right? What else, ma'am? We provide you all India test series for your revision apart from mock test and Tattva modules. So all these things we provide you, right? Someday I'll also show you how Tattva book looks like, right? Maybe in the next lecture only, right? Now all these things are provided to you, right? Even if we try, we won't be able to provide it on YouTube, right? Okay, that will create a mess. But there everything is well structured, right? Everything is on our own platform, right? Moreover, only those students are there which are sincere. So you're competing with the sincere students, you are competing, you know that where you lie and how much you need to put more efforts. On daily basis, you have leaderboards, right? So it makes the study more systematic, right? There is proper deadline, right, to complete the chapter for teachers as well. And best part is you have feedback option for the teachers, right? So that is the reason, right, that even if you feel that, okay, I'm not happy with this teacher, you can give the feedback and your feedbacks are appreciated, right? Okay, understood? Yes. Says today you look more positive and are new positive vibes. Thank you so much, Bharadwaj. Thank you, future IITian. Yes, thank you so much, guys. Now I would love to see you all in the Sigma batch as well, right? Where it is a more homely feeling, right? Because there it is a closed room where we and our family of Sigma batch is there, right? Okay, yes. Okay, then, guys, bye bye. Take care. Now, please don't forget to write it down in the comment section. Hashtag same but different, and also your homework. I'm waiting for your comments, right? Okay, bye bye. Take care. See you all in the next class. Bye bye.